Given the position of some object as a polynomial function of time t, we worked out the hidden units that are attached to each of the coefficients in that polynomial, and we're now ready to proceed to take the derivative of this equation. We call it the derivative of x with respect to t in order to find the corresponding instantaneous velocity of the object as a function of time. All right, so there's a rule for how to do this, and the rule is not difficult to prove, but I'll leave it to your calculus teacher to prove it. I'm just going to give you the rule here. So what we do is take the terms in the polynomial one at a time, and for each term, we do this. Okay, so each term is of the form ax to the b. A is the coefficient, like -3 or 4 or 9, and b is the exponent, in this case 2, or, what are our exponents here and here? We'll need to note that if we have t here, we recognize that that is t to the first power. We never write the 1 there because we always know what we mean, but it's really t to the first power. There's no t on this term though, but we know that t to the 0, or any number to the 0, equals 1. And we can multiply 9 by 1 and get 9. So 9 is the same as 9 times 1, which is the same as 9 times t to the 0. So we can always put a little t to the 0 here without changing anything. T to the 0 is just 1, so we can stick it in right there. Now we recognize that each one of these terms is of this form, where b is the exponent, b would be the 2, the 1, or the 0. And so the rule is to take the derivative of each term, you get a new term that looks like this. The new coefficient is the original coefficient a times the original exponent b. So we say that you sort of bring the exponent down to multiply it by the coefficient to get the new coefficient. Then the new exponent is the original exponent minus 1. So in this case here, our first term, we take 2 times -3 to get the new coefficient, and then 2 minus 1 gives us 1. That's our new exponent. So the first term here, the -3t squared, becomes -3 times 2 times t to the first power. And the unit, meters per second squared, just comes along for the ride. That doesn't change. Second term, we'll have 1 times 4 to give us the new coefficient. And then 1 minus 1 is 0, the new exponent. Again, meters per second comes along for the ride. Last term, 0 times 9 is the new coefficient, and then 0 minus 1 gives us minus 1. But this t to the minus 1 doesn't have any role to play because 9 times 0, anything times 0 is 0. So let's note that this last term here, the 9 term, what we call the constant term, because it didn't involve t to any power other than 0, the constant term disappears when we take the derivative. 9 is just gone since we multiply it by that 0 there. So our constant term disappears and we're left with these two terms. So we can rewrite it as velocity as a function of time is dx dt equals -6 meters per second squared t plus 4 meters per second. Because that t to the 0, that's just 1. So 4 times 1 is 4. And here we have our polynomial function of time for the velocity. Note that we originally had a quadratic function, then we took its derivative and got a linear function, t to the first power here. So taking the derivative of the quadratic got us this linear function. Let's now find the acceleration of this object as a function of time. It's instantaneous acceleration. We'll do that by taking the derivative again. So the acceleration of this as a function of time is defined as the derivative of the velocity with respect to time. We also call this the second time derivative of x, d squared x dt squared. This peculiar notation is how we indicate that we're taking the derivative of the position function twice. Note that the squared appears next to the d in the numerator, but next to the t in the denominator. That's just an old convention. Okay, so these are two equivalent ways to write the acceleration, dv dt or d squared x dt squared, the first derivative of the velocity or the second derivative of the position. What is that function? We'll just apply our rule again to these terms. So we'll take, let's see, This is t to the first power here, and the 4 times t to the 0th, because that's just 1, we can stick those in. And now apply our rule. We take 1 times -6 to get the new coefficient, and then 1 minus 1 is 0 to get the new exponent. Then here, 0 times 4 to get the new coefficient, and then 0 minus 1, -1. Well, 0 times 4 is just 0. So once again, the term that was constant, the constant term here disappears. And we can simplify that to see that what we have left is t to the 0. That's just 1, so this is -6 times 1. So just -6. We have simply a constant. We prove that the acceleration is, oops, I'm off the screen there, sorry. We've shown that the acceleration is just this constant, -6 meters per second squared. Let's, before we summarize, go back and check on the units here that we've been carrying along. Let's go back to this line. If this is supposed to be meters per second as the unit on the velocity, then each of these terms must have units of meters per second. This has to be meters per second plus meters per second equal meters per second. We can verify that it works since we have a meters per second squared attached to the 6 right there times t to the first, t in seconds. So it's meters per second squared times seconds. Seconds cancel out, and we get meters per second. And here we have 4 times meters per second times seconds to the 0. Well, anything to the 0 is just 1, including the unit. So the unit goes away. There's no unit there, just sort of a 1. So that is also meters per second plus meters per second equals meters per second. So our units still do work out when we carry them through this way. Likewise, down here, meters per second squared equals, of course, the meters per second squared on acceleration. All right, so to summarize here, I'd like to know what happened. We had a quadratic equation, took the derivative once to get a linear equation, then took the derivative again to get a constant. And you can compare these three to our constant acceleration equations. Since we discovered that acceleration for this object had been constant, then these equations should apply to its motion. So the first equation here, we can note a correspondence to the terms in our polynomial over here. In front of time squared is 1/2 acceleration. This is the coefficient of the time squared term. That corresponds to the -3 meters per second squared. This is the coefficient of the time squared term. Therefore, we see that -3 meters per second squared is identical to 1/2 the acceleration. And that's the significance of this little unit that was sitting in here. That hidden meters per second squared, it's there because this number represents an acceleration, half the object's actual acceleration. Likewise, v0 is the coefficient of the t term. Over here, 4 meters per second is the coefficient of the t term. Therefore, what does this 4 meters per second represent? Why is there a hidden meters per second on there? It's because this is the initial velocity. And the 9 meters over here represents your constant term, the initial position x0. So it's got a meters on it because it is a position. Then let's see, if we applied our rule, this rule here, to our constant acceleration equation, we can do that. Even though our coefficients aren't numbers here, they're variables, we treat them the same way. So if we take the derivative of this first term, we would do 2 times 1/2 the acceleration. So 2 times half the acceleration would give us the acceleration. Then 2 minus 1 is 1, gives us a new exponent 1. So the derivative of 1/2 at squared gives us at. Next term, this is t to the first, so 1 times v0 gives us v0. Then t to the first minus 1 gives us t to the 0, which is just a 1. So the derivative of v0t just becomes v0. And we know that the derivative of a constant is 0. So it becomes 0 over here. So this constant acceleration equation is indeed the derivative of this one. And if we take the derivative again, at just becomes a, and that constant disappears and becomes 0. Making the correspondence once more, we see that the coefficient of the t term is a, coefficient of the t term is negative 6 meters per second squared. So this is indeed our acceleration, negative 6 meters per second squared. And this, the 4 meters per second, that corresponds to our v naught. And again, there is our acceleration.